All right, let's get started. Okay, so in today's lecture, we plan to talk a little bit more about this binary arithmetic. We will be focusing on this addition. So we are going to be building some adders. One of the adders will be truly cool. It's called CLA, care look ahead. After that, we'll focus on the so-called ALU, arithmetic logic unit, which is the compute core of a microprocessor. Right. Some logistical issues. First of all, some of you might have already seen that we just released the first batch of this raw quiz scores on CMS. By raw, I mean that this is not processed yet, in the sense that in the end, right, I promise you, in the syllabus, right, we're going to drop some of the lowest score, right, in the end. This is just unprocessed quiz scores for the first few lectures. And since actually many students joined this this course late, for the first quiz, we actually gave a full mark to everyone. I think that's the lecture 2. Okay. And we'll most likely release another batch in a month or so, later this month. Okay. And we have pre-lab 3A, right, due today, and also lab 2 report is due tomorrow. This is actually probably the only week where you guys have to turn in 3 things. Okay, I know that you are all busy, but I promise you this is the only week. Right? In most weeks, you only turn in at most 2 things, right? 1 lab assignment and 1 homework assignment. Okay. And also there's a TA lab Verilog course tutorial. Nikita is going to be leading the discussion. This is supposed to happen last night, right? But actually the attendance was pretty low. That's why Nikita decided to reschedule this to Wednesday night. I highly recommend this session because that is based on some of the posts that we are seeing on Piazza. Right? So many of you are having some issues debugging your Verilog code. And this tutorial is meant to address some of those issues. So it's hopefully going to be a 1 hour well spent for both sides. Hopefully this is going to help you minimize your debugging time. Right? Hopefully you can solve some issues on your own after attending this tutorial. If you have a conflict, right, so make sure you watch the recorded video. Okay. All right, so let's get to the real meat. First, a quick review. At the end of the last lecture, we talked about this overflow, right, for 2's complement numbers. This 2's complement, right, the nice thing about 2's complement is you can just use the regular, right, the vanilla addition that we are familiar with unsigned numbers, and it just works. Okay. Although there's a caveat, right? In many cases, we are adding this fixed size numbers in the sense that we have a fixed bit width. In this case, right, for the examples on this slide, we are adding a 5-bit, right, numbers. This is our fixed size. Let me remind you guys about 2's complement again. Right? For a 5-bit 2's complement, or maybe you can tell me. So what is the most negative number for 5-bit 2's complement? 5-bit 2's C. What is the range? Minus 32. Are you guys sure? 5-bit, right? Okay. We can, for unsigned, right, with 5-bit, we can represent the range we can represent is 0 through 31, right? And with 2's complement, obviously we cannot, right, soar up to 31. We have to spend, right, at least half of it for the negative part. Very good, right? So actual number, right, this is the lower bound, right? It's minus 16, right? Minus to the 4. Upper bound, what's the upper bound? 15, very good, right? Not 16. Okay, we'll look at this addition, right? We are adding up 8 and 9. Right? The expected value with right, so with the decimal addition is supposed to be 17, right? But since we only have 5 bits, 17 is out of the range. 17 is greater than 15, right? It's out of the range. That's where we are seeing this overflow, right? That's where we are seeing this wraparound. We're seeing minus 15 instead. Same thing here. if you look at this example, the expected value is supposed to be minus 17. It is also out of the range because we can only represent minus 16 with 5 bits. So that's where we are seeing another wraparound. Okay, so this is where overflow happens. Again, the bare definition of overflow is when we are adding up two operands with the same sign, and somehow in the end, the sign of the sum is flipped. It's different. That's where we have an overflow. And this is the one way to detect this in hardware is by checking the carry in to the MSB, the most significant bit, and the carry out from this bit position. If they're not the same, then we have an overflow. Okay, let's try to analyze it a little bit more. Okay, with another example. Okay, so these are the examples, right? 5-bit examples, and this is a definition and the test in hardware. Last time I also asked you guys to do a quiz. Okay, so this is the one. Right? This is the example that you guys worked on right at the end. Is there overflow? Should be obvious, right? I already gave you the answer. I already gave you the sum. Yes, right? Obviously, we are adding up two positive numbers and we end up with a negative number. So with this 2's complement to tell, right, whether we have a non-negative or negative number, it's the same thing, right? Just look at the MSB. It's a 1, that's negative. Okay, answer is yes in this case. How about the other one? Yes or no? No, right? Because in this case, we are actually adding up one number is negative, right? The other one is non-negative. The other one is positive. So the answer is no. But why is that? Why is that? How come, when we add up two values with different signs, with opposite signs, there's no overflow? What is the intuition? Very good. Okay, I think Steve, Mitchell, I guess you guys are saying the same thing, right? There's no way that you can get out of the range. Okay, in this case, maybe we can come back, right, to this example where we already have the decimal numbers. Okay, actually, let's use this one, since there we have two overflow scenarios. Right, in this case, so the sum right over here cannot be more negative than this number, right? And cannot be more positive than this number. Make sense? Again, the sum cannot be smaller than the first operand and cannot be greater than the second operand. That's where when you add up, right, so two values with different signs, there's no way that you will end up with an overflow. It's going to be end up, something in the middle, right? So that's the intuition. Again, no overflow here. So we also talk about the other test, which is more efficient in hardware, right? So we look at MSB, okay, and we look at the carry in, right? In this lecture, we'll see a lot of shorthand. Let's use CI to indicate the carry in, and CO to indicate the carry out from the MSB and the carry in into the MSB. If these two are different, we're saying that there's an overflow. Okay, so look at this case, this example on the left. Okay, so we do have a carry in, right? There's a carry into the MSB, but there's no carry out of MSB. Indeed, right? So there's a overflow. If we look at this case, there's also a carry right into the MSB. There's a carry into the MSB, and there's a carry out of the MSB. So they're the same. In this case, there's no overflow. Okay. Why is this? Why does this test make sense? Any idea? Let's just try to break it down, right? We just mentioned that there's no way that when we are adding up two values with different signs, overflow will occur. So let's just focus on two scenarios. First, if we have, we don't care about this, right? Let's just look at this is MSB, okay? Right, this is, let me write it down here, MSB, okay? If there is a carry in, Okay, if the CI is 1, and there's no carry out, okay, in this case. Okay, obviously, what do we have? We're gonna have 1, right? There's 0, 0, right? So if there's a carry in, whether there's a carry in or not, there will be no carry out. Make sense? Right? And if you look at the sign bit or the highest bit, right, for the sum, it's gonna be a 1 in this case. Okay, and obviously there's an overflow, right, because the sign is flipped. This is the one scenario, right? Second scenario, if you're adding up two negative numbers, okay, when do we have a scenario where the C in and C out differ? When we have, because in this case, regardless, there will be a carry out, right? In this case, again, this is MSB, okay, and we don't care about the last significant bits. And the only case where we have a difference is this is CI, this is 0, right? And in this scenario, the sum bit, right, on the MSB is going to be 0. So the sign flips again. That's where we have another overflow. Okay, and we're going to be using this in Howard. All we need to do in Howard to detect overflow is we just have to do XOR, right, on the MSB. We do the exclusive OR, right, on the carry in and carry out. That's it. And this is going to return the overflow flag. Okay. Any questions about overflow? Okay, good. Let's move on. So now that we have, hopefully all of you are now familiar with the basic of binary arithmetic, right? How we do additions, was 2C, right? 2's complement, and also how we do the addition by hand, right? Manually. So now let's look at how we build this in the actual digital circuit. First, let's look at a 1-bit adder. So this is something that we have already seen, right, in the past. I showed you guys this table in the very first lecture, right? We have 3 inputs, A, B, carry in, and 2 outputs, sum and carry out. And this is the corresponding circuit, right? And this is the sum bit, right? This is a circuit for sum bit. When do we have a sum? Here we have 2 XORs, right? And these are basically a 3-input XOR, right? Stacked, right? We basically stack 2 XOR, 2-input XOR. Think about the definition of XOR. What is XOR? Close, right? Very close. We also introduced this notion of parity at a certain point, right? Very good, Jacob. Right? If you have odd number of ones on the input side, then we have a 1, right, on the output side. That's the definition of parity. We actually call XOR a parity gate, which is true here, right? For addition, if a single one, we have a 1, right, on the sum bit. If you have 3 ones, we also have 1. Right? If an even number ones, then the sum bit is a 0. Okay, so that's where we are seeing this XOR. And this is the carry out. Okay. Also, later on, we're going to be analyzing the delay pretty soon for this kind of adder circuits. So here's my assumption. Let's say, each gate just take 1 nanosecond, right? All of this gate, all of this. What is the longest pass here? Later on, we'll just call it critical pass. By critical pass, I mean the longest one, the longest propagation delay. It's obvious here, right? Longest one is what? Just 2, right? We're going through 2 levels. Of course, one may argue, I'm making some assumption here. XOR, to some extent, right, is indeed more complicated than OR and AND in terms of CMOS. But let's just make this assumption. And we'll come back to this. Okay. Remember that basically our 1-bit adder is going to take 2 nanoseconds. Okay. And also this is called full adder. The reason we call it a full adder is because the input side also includes carry in. The moment we include carry in, we call it full adder. If you drop carry in the textbook and in some other cases, you may see something called half adder. That's where we don't include the carry. Okay. All right, so this is a 1-bit full adder. This is the circuit, right, on the left. In many cases, we are going to use this as a building block, right? We're going to be using it pretty soon. And this is just too complicated. Instead, we can just draw a symbol like this. Since we usually add right from the right to the left, so that's where the carry flows from the right to the left. So this is a convention that we're going to use. The inputs are coming from the top, and the sum is going out at the bottom. This is the notation and convention that we're going to assume. And later on, if you want to further abstract away some of the details, like this input and carry in, carry out, we are going to use an even simpler symbol like this. We just call it FA, means full adder. Okay. All right. So now that we know how to build a 1-bit full adder, so let's look at how we build a multi-bit binary adder. The idea is actually pretty straightforward, right? So all we need to do follow is we look at each column, right? Each bit position, and we try to stack up, right? Cascade these adders. That's the base idea. And we do need to propagate a carry, right? Okay. First, let's introduce some additional variables or some additional terms, right? We already know the notations. We already know that for each, let's focus on each column, right? Given the bit position, basically each column, we have 3 inputs depending on the actual index of the bit position, which is called AI, A sub I, B sub I, and C sub I. Right? CI means the carry in. This is our convention here. I think the textbook might be using a different convention, but in this lecture, we're going to be using, when we say CI, not CI minus 1. Right? CI means the carry in into the bit position I. And CI plus 1 is a carry out from the bit position I. Of course, SI, right? S sub I is the sum bit. Okay, so these are the notations. And of course, the carry out, right, of a bit position is basically carry in for the next one, since this is a basic cascade. Given these definitions, let's see how we use this 1-bit full adder to build a 4-bit adder. All we need to do is to cascade them, right, from the right to the left. And we just need to propagate the carry. Okay. What do we put here? Before I answer your question, Alma, let me ask the class one question here. Right? We're doing addition. What do we do with the very first rightmost adder? We just need to put a 0 here, right? Basically, the first one, in the end, after we optimize the circuit, it's going to be end up right with we're going to end up with a half adder. We don't really need a full adder here. If you only need a circuit that does addition. Okay. Alma, you're asking about the carry out, right? What about carry out? Can you clarify your question?
Yeah, I mean, like you could see at the top that there's still enough. Like, let's say you only have like a 5-bit adder and there's overflow, like
this one?
Happen, yeah, or nothing can be done about it.
Right. So yeah, good question. Yes, right now we in many cases we do want to preserve the carry out from the MSB so that we can detect overflow. We'll talk about later, right? How do we deal with overflow? In many cases, we just need to detect it. But if this is indeed a problem, we'll let the microprocessor know. There is certain thing called exception that we can discuss later. Okay. For now, all we need to do is we do want to preserve that carry out in some cases so that we can detect overflow, and all we need to do is to flag that if an overflow indeed occurs. Right. Okay. So this is the 4-bit adder. All we are doing is to cascade, right? So this 1-bit full adder altogether. So that's where we have so-called this actually so-called repo carry header. But one more time, let's look at the delay. And we just agreed that each full adder takes 2 nanoseconds, right? what is the critical path here? What is the longest path today? For 4-bit, this is a carry. This is basically a repeal carry adder. Just 8, right? Okay, very good. Just 8. And we put a 0 here. Okay. If we are doing addition, we just put a 0 here. Okay. Like I mentioned, it's called repeal carry adder. We just got RCA. We just take the acronym. Okay, so what about subtraction? We just mentioned addition, right? Just discuss addition. How about subtraction? How do we do subtraction using the adder that we just built? Any ideas? Over here, we're doing 104, right? Minus 17. Okay, so you guys are ahead of the game. Okay, very good. Let's talk about carry in later. First, let's do this step by step, right? To make use of the adder, all we need to do is, right, 104 minus 17 is the same as 104 plus minus 17, right? Obviously, right, this is true. So that's the idea, right? But how do you get this one? Okay, so how do we go from here to here? Last time we talked about how to convert, right? How to do this conversion for 2C, 2's complement. Given x, right, you want to get minus x. What are the steps? We first flip all the bits, and then we plus 1, right? So this is the conversion. So how we get 2C for minus x. Let's just do the same, right? We are doing a minus b now. All we want to do is, right, again, we are doing a minus b. So we're going to convert it to a plus minus b. And minus b is the same with, right? So this is b naught, right? By b naught, I'm talking about, right, we are inverting every single bit, right, in b naught plus 1. Okay. So all we need to do is to add some inverters on the second input. But somehow we need to do this plus 1. Right? Okay, so first we can extend this addition, the RCA repeal carry adder with this 4 inversions, right? Inverters. And we are missing something, right? We need to somehow plug in this 1. Where do we plug in the 1? Mux. We need the mux. Mux in where? Okay, very good. Right. Devlin, Steve, Mitchell, you're saying that instead of putting 0 here, remember that we had a 0 here, right? The first adder, the first full adder is sort of underutilized, right? You can put a 0 here. So instead, maybe we can just put a 1 here. And that's it, right? That's where we get the plus 1 by using the carry in on the LSB. Make sense, right? So that's how we do a subtraction using this repeal carry adder. And some of you are mentioning mux. I guess you're thinking about how to further combine this, right? How to combine addition and subtraction. How to do like a dual purpose circuit. Okay, so this is actually our next task. First, any question about this? How do we do a subtraction using this set of letters? If not, okay, let's look at how do we do a dual purpose one. This is where we make use of the muxes, right? So here the goal here is, we don't want to just do addition or just subtraction. Instead, we want to be able to handle both operations. This is where we introduce the muxes. Okay. Right. So finally, right now that you guys are seeing where we are using muxes in the actual circuits, right? We have been practicing different, right? We are practicing muxes a lot, right? Mux is indeed very useful because this is where we use it to select inputs. If you are doing addition, we take this path, right? We take the original B. Otherwise, we take the inverted B. That's how we use the mux. And we have this select signal. This one, So this is a so-called opcode or operation code. This sub is basically a signal, 1-bit signal that's included as part of input. Okay, it's called an opcode. If this is 1, we are doing subtraction. If the sub is 0, we are doing addition. As simple as this. Okay. And this is so-called multi fan out. Right? See, if you look at the signal, this signal is driving multiple muxes. See here, same signal driving, in this case, 4 muxes. Okay. So again, it's 1, then we take the original B0, B1, B2, B3. Otherwise, we take the flipped version. And we also make use of this. Right? The nice thing about this is 1, we can just connect it to the carry in. That's where we get the +1 for subtraction. Any questions about this? Hopefully this is intuitive enough, right? Okay, very good. Actually, this RCA is just one of the many different kind of adders that we can have. Right? One thing that I want to briefly mention is there are actually many different kind of implementations for adder that makes trade-off between performance with a delay and the circuit complexity, which is area power. The RCA that we just look at is actually the simplest kind of adder. Right? All we need to do is to stack up, right? To cascade these 1-bit full adders, and we're done. But the downside is it's pretty slow. You can imagine, right? We need to propagate this carry all the way from the right, from the LSB all the way to MSB. That's where we get the critical paths, right? For a 4-bit adder, we have 8 nanosecond, right, delay. Let's say the microprocessor use 32-bit word, so this is our fixed size. For a 32-bit adder, how much delay do we have to spend on a single addition? That's going to be 64 nanosecond, right? Let's also keep this number in mind, because I'm going to introduce a faster adder pretty soon. Like I mentioned, there are actually many different kind of adders. There's actually a zoo of different adders. Okay, I cannot even count. This one, that is a computer arithmetic, is another very rich subject, very rich topic. We easily have like 1,000 different kind of adders that treat us different kind of metrics like delay, area, power, and different things. Okay. What I want to introduce next is a pretty interesting adder. So this one is faster, but more expensive in terms of area. It's called carry look ahead. Okay. The shorthand is CLA. There are also other kind of adders that you may encounter in other courses, like carry select, maybe in some of our homework. Okay. I may introduce a problem where you can exercise and play with some other adders, carry save and prefix sector, etc., etc. There are a lot of different adders. Okay. So just want to make sure that you guys know this. Yeah, we are not going to talk about there's different variations. This is outside the scope of this class, but there are indeed many variations, and this is a very rich topic.